Mechanisms are important because it gives you information as to what chemicals are responsible for the speed of the reaction. Mechanisms are important because it shows you the step-by-step sequence in which reactant converts over to product. With a mechanism, you can figure out a shortcut. You can figure out maybe what steps to bypass as you're trying to produce more chemicals. For example, you're in a pharmaceutical lab, you're one of the pharmaceutical scientists, you're trying to design a drug that might alter or hinder maybe a virus like COVID, and you want to make that an efficient reaction. Well, remember, you're designing the drug, you're not actually resynthesizing the virus. So you're designing the drug. What chemicals come together to make that target drugs? And so if you know the mechanism by which the chemicals interact, maybe you can find a shortcut. Maybe you know what type of catalyst to introduce to make that reaction more efficient. Or you're studying a reaction like we did in the 1980s. The 1980s, we actually found out that our atmosphere had a depletion of the ozone. Ozone is a chemical, O3. It's this chemical right here. It's bent. Its Lewis structure looks like this. It's poisonous here at sea level because if we breathe it in, the electrons on the ozone will react with our body, our tissues, and cause radical formation. Not good. But that same property means that it can go up into the atmosphere and it will absorb photons that have high energy. Okay, 340 nanometers, 320 nanometers. Remember, the smaller the wavelength, the more energy it has. If it has more energy, then if it ever hits our skin, it can break the bonds of our DNA. If it breaks the bonds of our DNA, then it's going to cause damage. And when our DNA starts to mutate, not mutate, but duplicate itself, it's undergoing mutation. Cancer might arise based on that. So that's why we need ozone in our stratosphere, because it's sort of like a sunscreen for planet Earth. So let's take a look at this right here, and let's see exactly what's going on in terms of the mechanism by which we figured out how ozone was depleted when we discovered it in the 1970s, and then we sort of proposed the mechanism in 1980. In fact, a scientist, I think it was Harvard or Yale, okay, kind of figured it out. He's since moved to UC Irvine. He's a scientist there. His name is Molina. He got the Nobel Prize somewhere in the 1980s to early 1990s because of this work right here. So here's a cartoon of what our atmosphere looks like. Okay, you guys see the landing of the rover last week. It was pretty amazing. Okay, the atmosphere on Mars is pretty thin, so it's pretty amazing that they can get the helicopter to go up, especially since the only reason we have life here on planet Earth is because of our atmosphere. The air causes a medium by which we can float, just like we float easily in water. Okay, if it's a vacuum, then we can't get that lift. We need like propellers, or not propellers, but rockets, like when we go into space. But anyway, that's for another story. Ask your astronomy teacher. But in this particular case, this is what our atmosphere looked like in planet Earth. We have the troposphere, okay, slightly above Mount Everest, and then we have the stratosphere. And that's above Mount Everest all the way to about 50 kilometers. And then we have the mesosphere. The stratosphere is where the ozone layer is found. And it sort of sits there, okay? And it's important that it's at that elevation, because if it's in that elevation, then it's not down here where it can cause damage to us. And what happens is that when radiation comes, then the ozone is responsible for blocking that damaging radiation. And this is what we call the Chapman cycle. It's the mechanism by which ozone is going to be depleted and regenerated. Ozone actually gets depleted to oxygen atoms and oxygen diatomic, oxygen molecules, the ones that we breathe. So this is basically it. But the mechanism is started by the chemical absorbing photons. So here we have photons, 242. That's really small in terms of the wavelength, 242 nanometers or less. The photons are going to get absorbed by the oxygen. The oxygen cleaves. You get the oxygen atoms. The oxygen atoms react with another oxygen molecule. Remember, diatomic oxygen is the one that we breathe here in at sea level. And then it forms this ozone. Okay. Now, if we just had oxygen in our atmosphere, it would basically filter out light of 242 nanometers and less. But damaging radiation is about 340 all the way to a smaller wavelength. So if we just had oxygen in our atmosphere, we would not be able to filter out the 340 nanometer radiation. But ozone does that. 320 nanometers or less, ozone will absorb, and then it'll cause that O3 to cleave to oxygen and an oxygen atom, or the ozone, if it doesn't, it can combine, it'll cleave, and this will form O2 and another oxygen, and you get 2O2 in this particular case, 2O2. Okay, so an ozone will cleave, that oxygen will react with another oxygen atom. So you get the O2 that has been cleaved, and then the oxygen binds with another oxygen. So these are the, these are the steps. Sorry about that. Sometimes I put my hands everywhere. These are the steps by which O3 gets converted back to O2. And so this is the removal step of ozone, okay? So ozone itself will be consumed through different mechanisms in our atmosphere. This is just a movie showing you what's going on. You guys could watch it if you go to the Google Drive and do this. Okay, just sort of explains what's going on here. You got oxygen, nitrogen, and in this particular case, let's see why the volume's not working here. Well, it basically shows you what happens to the oxygen as it breaks off, and then it reacts with chemicals. Anything that removes ozone, O3, from the stratosphere is going to be dangerous to our environment. Okay, so here's the reaction again from the Chapman cycle. Notice that that activation energy is only 19 kilojoules. It's not very high. The energy required, the activation energy required to take ozone to O2 is only 19 kilojoules, not very high. It's an exothermic reaction. That energy, delta H of the reaction is right here. Okay, the reactant, this is just a relative scale right here. Okay, we decided to put O3 at 0, but it's relative. Why is it relative? Because we just want to know the differences in energy. How does the O2 energy compare to the O3 energy? In fact, that energy is minus 392 kilojoules. The activation energy in the reverse direction is 411 kilojoules. So you can read all that just based on this diagram. Okay. And again, it shows you how that works. But although ozone will somehow react with oxygen in our atmosphere and it's removed, it also gets regenerated in our atmosphere. But there are other chemicals in our atmosphere that will remove ozone and it's not going to be available to absorb the damaging radiation. Water vapors, for example, will do that. Water will break at the very high um, elevations. It'll form radicals. These radicals can now attack ozone, and what you get is you convert ozone to O2. So these are pathways to destruction of ozone. Nitrogen also does it. These are nature's way of removing ozone from our um, stratosphere. We can't do anything about it. It was part of the chemistry in our atmosphere for millions and millions of years. Okay, but one chemical that was introduced past probably what 100 years is CFCs, chlorofluorocarbons. Chlorofluorocarbons was our answer to ammonia. What we needed was we needed a chemical that we could stick in coils that will reduce the temperature of a container. Okay, if you put it under high enough pressure, these chemicals, and then you expand it, the process of expanding causes that temperature to drop because it removes the energy from whatever it's in contact with. That's how a refrigerator works. You have a pump in your refrigerator, it compresses these chemicals, and then in the process of releasing that chemical into the coils, it expands. In the process of expanding, it absorbs the energy in your refrigerator, and so the temperature drops, and then the energy gets dumped out in the back end. That's why your refrigerator's warm in the back end, and then it compresses the fluids again. And in the old days, we use ammonia. The problem with ammonia is that if you have an ammonia leak, it could be very damaging. It could react with things, and it's not very nice chemicals to be in contact with. So I think it was DuPont or Dow, that one of these chemical companies that came up with a chemical that was inert. What does that mean? It means that if you spill it, it's not going to react with anything. It's inert, just like Teflon. Okay, so that was good because then you can make that as your refrigerant. You can put in these coils, you can compress it, and then when you release it in the coil and expands, it absorbs the energy from your refrigerator, and then it dumps the energy to the outside, the back of the refrigerator, and then it gets compressed again. Okay, so for those of you who are engineers, you guys will learn all about that in terms of the compression expansion cycle. But the neat thing about these chemicals, Freon, was that it spills. Okay, you're putting in the Freon in your refrigerator, you're putting it in the manufacturing plant, it spills everywhere. It doesn't matter because it'll evaporate. It goes nowhere. Okay, it's not going to react with anything. It's not going. You're not going to get poisoned by it because even if you breathe it, it's not going to react in your body. And so that's what they thought. Until they realized that these things, where does it go? Okay, it's pretty light in terms of the chemical. It turns to gas, so it sort of goes up into the atmosphere. Where it was going was in the stratosphere. In the stratosphere, it sort of sits there. And then in the winter days, it sort of collects on the ice crystals in our stratosphere. So as it collects in the ice crystals in our atmosphere, it just sort of sits there. And then in the spring, when it starts to thaw, then the radiation from the sun cleaves the CFCs, and you get these radical formation right here. These radical formation, and then they attack the ozone. Okay, they attack our ozone, O3, and because we've accumulated so much of these chlorofluorocarbons, we didn't know that they were actually up there in our stratosphere. We started to see in the 70s and 80s that the Antarctic has a huge accumulation of ozone, that there was a hole in the ozone layer. Okay, they noticed that, and they're trying to figure out why does it only occur right around maybe September, October. Okay, why does it occur? There's a big ozone hole right around September, October in the Antarctic, and then it closes up. But each year was getting bigger and bigger, and the reason why that it happens again, remember the Antarctic is in the South Pole. It happens around September and October is because the Southern Hemisphere, September, October is their spring. Keep that in mind. So in the wintertime, our summer, their winter, the atmosphere would have these ice crystals. And then from winter to spring, it starts to thaw, and then it releases this chlorofluorocarbon that have been cleaved, and then they attack the ozone. And so as it attacks the ozone, there's less ozone in the Arctic, the ozone layer, and you start to see this hole. And a guy by the name of Molina, the scientist, figured out the mechanism by which that occurs. So it says right here, there's about 10,000 ozone that will break down for every chlorine radical, for every chlorofluorocarbon. So of course we started to put regulation as to what chemicals we can put in our hairspray, because there was a lot of freon in our hairspray back in the 50s. We had regulations as far as how to handle freon for our cars and refrigerator. In fact, you had needed a license to do that. You couldn't just buy it off the store anymore. Okay. I think since then we found substitute for chlorofluorocarbons that aren't as harmful to our ozone, but still, that's the story of ozone. I sort of went off in a tangent here, but I figured you guys needed to know that, because it seems like every time we make technological advance, we tend to damage our environment. And so we gotta remember that sometimes these technological advances has consequences. We gotta know what the long-term consequences are, so that even though it will help us in the immediate present, it might hurt us in the long run, and we need to figure out ways to remedy that so it doesn't hurt our future generation. Anyway, this is what happens when you have chlorofluorocarbon. Remember, this is about 19 kilojoules right here. Look what happens when you have chlorofluorocarbon. It places a catalyst, and it lowers that activation barrier even lower. It makes it even lower, and it makes that reaction occurs even faster. That's why it's about 10,000 ozone that will get consumed for every one chlorine radical, which comes from chlorofluorocarbons. Okay. So there's a whole bunch of movies on that. Anyway, when we're studying mechanism, you got to remember that each step in a mechanism is called an elementary step. The series of elementary steps, when you add them up, gives you the overall stoichiometry. The overall stoichiometry is the summation of the elementary steps, but the elementary steps are the different steps. Remember, we had this. So this is step one, from here to here. That's one step. This is the second step. This is the third step, the product. And so this would consist of 3 elementary steps. The overall reaction is this reactant converting to this product. That's the overall reaction, but it takes 3 elementary steps to get that overall reaction. Okay. The sequence of steps which describe an actual molecular event, those are your elementary steps. The stoichiometry is the total when you sum it, and you cancel the intermediates in the net reaction. Okay, and again, I've already told you this, scientists want to know about mechanism. It's one important thing that is of interest to scientists, especially if you're going to design a chemical that is needed. You want to know the mechanism. Organic chemistry, you're notorious for trying to figure out what mechanism will take you from point A to point B. Okay, here's the Chapman cycle. This is the mechanism. It's got 2 elementary steps, 1 and 2. And the first elementary step is ozone breaking down to oxygen and oxygen atom, and then oxygen atom reacting with ozone again to produce 2 diatomic oxygen. When I say diatomic oxygen, I mean that. Okay, when I say the oxygen atom, I mean that. When I say ozone, I mean that. Okay, so the net reaction is the following. This oxygen cancels with this oxygen, and your net reaction is these 2 forming these 3. That's your net reaction. The oxygen atoms or the intermediates. Why? Because it forms, this is probably a two-step mechanism, probably looks like this. Okay, this is the first step. From here to here, intermediate, and then intermediate to product. So two-step mechanism, 1, 2, and your intermediate is going to be oxygen in this particular case. Okay, the intermediate will be produced in the first step and then consumed in subsequent step, in this case, the second step. So let me do this real quick, clear this. So these are the elementary step. The A, the I, and the J are the coefficients, okay? And you look for the slow step, because the slow step is the step that determines the rate of the reaction, okay? The slow step is what we call the rate determining step. Rate determining step. And it's the slow step that is responsible for the rate of the reaction. It's the slow step. It's the rate determining step that is responsible for the rate of the reaction. Okay. Remember I told you that the stoichiometry, the coefficient in the stoichiometry is not responsible for the rate, but the coefficient in the elementary steps, these are elementary steps now, these are elementary steps, are responsible for the rate. Think about that. The coefficient in the overall stoichiometry are not necessarily responsible for the rate. The coefficient in the elementary steps are responsible for the rate. So you need to know the mechanism in order to figure out how does the chemicals relate to the speed of the reaction. The rate of the reactions is directly proportional to the concentration of the colliding species. Okay, that's why you need to know about the elementary steps, the individual steps that leads to the product. So let's take a look at the second reaction. This has 2 steps again. Both are elementary step. The first step is the slow step. This is the slow step. If you want the overall stoichiometry, you'll see that NO3 is an intermediate. And that's about it. Okay. It's produced in the first reaction, consumed on the second. The net stoichiometry is 2NO2 plus O3 goes to N2O5 plus O2. That's your net stoichiometry. The first step in that elementary step is the slow step, and it's the slow step that determines the rate. So I can tell you that the rate is equal to K, and you figure out K based on the Arrhenius equation. And the chemicals in that slow steps are NO2 and O3. Look at the coefficient. NO2 is 1, O3 is 1. That right there is your rate law. It's that easy. If you know which is your slow step and you have your elementary steps, okay, you have to know that. That would be your rate law. Of course, you need to figure out what K is. Okay, so let me clear this so that you guys can see that. It's that easy. Well, not that easy. You get into more complicated scenarios. Okay, in a series of steps, the slowest step determines the overall rate. Okay, and the mechanism for a reaction, the slowest step is called the rate determining step, also known as RDS. So when I say RDS, I mean the rate determining step. Okay. Now, if your rate determining step is to the first, and that's because A goes to product and there's only one A, then that is your order. That is your order. It's got to be an elementary step. It's not your overall stoichiometry though. Okay. Sometimes your overall stoichiometry coincides with your elementary step, but not always. But if it does coincide with your elementary step, then yeah, you use the coefficients in that stoichiometry, but only when it's the same as when the stoichiometry is the same as your elementary step. So whenever you take the chemical to the first power, we say it's first order. And it's basically called unimolecular. Uni meaning one, unimolecular. Here's a chemical, say 2A, goes to product. Here the coefficient is 2 in front of A. That's second order, okay? Second order, or maybe A plus B goes to product. And again, that's your elementary step. That's key. So it's A to the first, B to the first, and times K, that's your rate law. And here, because two chemicals are colliding, then we say it's bimolecular, second order. Second order overall. For the first example, second order in A. Second order, in the second example, it's first order in A, because notice the coefficient of A is 1. First order in B, second order overall. Bimolecular overall. Takes 2 of the chemicals to produce a product. Let me clear this up. Let's take a look at third, where 3A goes to product. Now, this is a rare reaction because 3 things colliding at the same time. It's like if we had a 3-way accident, 3-way collision in the freeway. More likely, what will occur is one car will undergo one collision, unimolecular, or maybe 2 cars will collide, bimolecular. 3 cars colliding at the same time happens not as often. Okay, happens not as often. This is an example of a termolecular, 3A going to product. Again, these have to be the elementary steps, has to be elementary steps. Or maybe 2A plus B goes to product, or A plus B plus C going to product. So in this particular case, what we have here is here, third order, like in triple, it's termolecular. Here, second order in A, second order in A, first order in B, third order overall, And then here, the last example, first order in A, first order in B, first order in C, third order overall. The order is the sum of the superscript. Okay, the order is the sum of the superscript. So that's what we have right here. Pretty basic. I hope you guys remember that. You guys will see that again. Termolecular, again, like I said, it's sort of rare. Oops. Okay. Why is the rate determining step important? Reason why rate determining step is important is because you guys probably been driving in the freeway, probably not as much this past year, but in previous years, maybe you're going up to Bear Mountain or Mammoth, and you're going up a hill, an incline. Well, if it's a 1-lane road, then the slowest car up ahead determines the pace of that group of cars behind. It's the rate determining step. The slowest steps determines the speed of the reaction, because you can't go any faster than that slow step. You can't go any faster than this slow moving vehicle. In other words, that's why that slow step is called the rate determining step. It governs the speed of the reaction. Doesn't matter whether the reaction behind it are fast, they get up to that slow car, they get back to that slow step, they stop until that thing paces itself. If it can overtake that slow car, then it can go on, but basically the speed of those group of cars is based on the slowest. That's why it's called the rate determining step. Here's another example. Okay, in this example we have 2 elementary steps. Again, make sure that you know how to write the overall stoichiometry. The overall stoichiometry is based on adding the elementary steps and canceling out the intermediate. In this particular case, you can spot the intermediate because it's produced on one reaction, consumed on the other. They cancel out. So in terms of the intermediate, NO3 is an intermediate. Okay. And I think that's about it. Look at NO2 though. Look at NO2. It's formed both. You have it both on the reactant and the product, but it's not formed in the early steps. Okay, it's introduced in the early steps and then reformed in the later steps. That's your catalyst. So your catalyst is NO2 because it's introduced in the first step, early step. It gets consumed, but it's regenerated in subsequent steps later. And so this particular chemical actually doesn't even show up. NOCO2, yeah, doesn't even show up. One of these chemicals, see, one of the chemicals is used, but the other is not. They cancel out. So one of the NO2 is a catalyst, even though the NO2 chemical itself is introduced as a reactant. So in this is a peculiar reaction because one of the NO2 is a catalyst in this particular case. Okay. So what is the rate law? If the rate law is this right here, the rate law is this right here. If this is my rate law, what can you tell me about the mechanism? If this is my rate law, notice there's a 2 right there, and that's NO2. Look at the first reaction. In the first reaction, you've got 2 NO2. That means that that's your slow step. Because you can take that reaction right there and use that to determine your rate law. If the second step was your rate law, then your rate law would look like this. Okay, it would look like that in the start. And I put an asterisk here because this needs to be more analyzed. Why? Because you can never have an intermediate in the rate law. You can never have an intermediate in the rate law. So what we need to do is we need to substitute NO3 out for chemicals that are not intermediates, catalyst or reactant. And I'll show you that shortly. Okay, I'll show you that shortly. But this would be a starting point if the second step were the rate determining step, but you would need more work. If the first step was your rate determining step, then yeah, this is the rate law because NO2 is part of the reactant, is part of the overall stoichiometry. Only chemicals that are part of the overall stoichiometry and catalysts can be in your rate law. Intermediates cannot. Intermediates cannot. Okay, so let's clear this. Which is the rate determining step? Based on this, we already said it's the first one. Okay, we already said it's the first one. Let's take a look at this. This is a one-step mechanism, super easy. If I give you a problem like this, then you already know what the rate law is. The rate is equal to K NO03. That's your rate law. And if I ask you what is the molecularity of that equation, you would say it's a bimolecular, first order in NO, first order in O3. Okay, first order in NO. Why? Because there's a 1 right there, even though I didn't write it down. There's a 1 right there. Second order overall, because 1 plus 1 equals 2. The elementary step coincides with the overall stoichiometry in this case. Let's take a look at the second one. Again, these are easy problems. You have a two-step mechanism. Two-step mechanism will give you probably a reaction profile diagram that looks like this. Okay. Where these things land depends on the energetics of NO2 and O3. It could be up there, it could be down here. I don't have enough information for that. But the information I know is that there is 2 humps in this reaction. The first step, the second step. The intermediate right here happens to be O because it cancels out. Okay, the intermediate right there. This is the transition step for the first step. This is the transition state for the second step. The first step is the slowest step. That means that the first step has the highest peak. Okay, it's going to have this type of profile. It's not going to have this profile right here. Because if it had this profile, then the second step would be the rate determining step. Your rate determining step is where your highest transition state lies. Let me make that clear. Your rate determining step is where your highest transition state lies. This is my rate determining step. My first step has got to be where my transition state is the highest. I've got two transition states in this reaction, but the first one the fact that the slow step is in the first step tells me that my transition state in the first step is the highest energetically. Okay, what is the rate law for this? The rate law for this is pretty easy. That's your elementary step. That's your slow step. Rate is equal to K03. It's going to be first order in O3. Okay, first order overall, unimolecular. So let me move on to a more complicated situation. Let's take a look at this. Here we have three elementary steps. A going to be, sorry, this is two elementary steps. This is the overall. And then our two elementary step is A going to intermediate, intermediate going to B. And our second step is a slow step. Let's say that this is an exothermic reaction, just for the sake of giving it a classification. Exothermic reaction means that the product is going to be lower in energy than the reactant. So our reactant is A, our product is B. Okay, we have two steps, so there's going to be two humps, and then our intermediate is going to be right here, intermediate. Look at where the slow step lies. Slow step, second step. So that better have a transition state that is higher than the first step. It'll look like that. Your activation energy is this right here, overall. But this is your first activation energy, E act for 1. This is your second activation energy, E act for 2. But the overall would be this right here, E act forward overall. And it's the second step that has the highest transition state because that's your slow step. Okay, and then I told you it was exothermic, so the product B better be lower than the reactant A. If it was endothermic, it would be higher. But your highest hill, the highest energetic transition state would still be in that second step. Okay, now how do you get the rate law from this? Here's where you have to learn a little bit of algebra. This is where algebra comes in. I'm going to be a little bit over my time. Okay, I'll probably take this to about 6:15 and then we'll probably finish off last time. That's why I'm extending the deadline. But you guys, after today's discussion, should have all the information to complete that worksheet over the weekend. So let me clear this up. So this is my slow step right here. So I'm going to write my rate law based on that slow step. Always write your rate law based on that slow step. Rate is equal to K, got to have a rate constant. And then the chemical in that slow step is the intermediate. And there's only one intermediate, so it's to the first power. So that's how I would start this analysis. Now, remember what I told you. An intermediate can never be in the rate law. It can never be in the rate law. So I'm going to have to do some math to convert this and relate it to A. Figure out how A is related to intermediate. You see this double arrow? This double arrow tells you there's an equilibrium between A and the intermediate. That means that you have an equilibrium constant. You guys will learn this in the next chapter, but just take this for granted. An equilibrium constant is equal to the products taken to whatever the coefficient is over reactant, whatever that coefficient happens to be. So in this particular case, K equilibrium, the equilibrium constant, is equal to intermediate to the first power, A to the first power. Why? Because these are one right here. These are one right there. So we have this equation. K equilibrium is equal to intermediate divided by A. Remember, bracket stands for molar concentration. Look at this equation right here. Look at this equation right here. Can't we rearrange that math so that we isolate the intermediate and say K equilibrium times A? It's just a mathematical transformation. We can do that. But now we can substitute. We can substitute this term right in here for that intermediate. And when we do the mathematical transformation, we get this. Rate is equal to K, which would be our regular rate constant for this kinetics, but we also have K equilibrium times A. But these guys are just constants. A constant times a constant is just another constant. It doesn't change unless you change temperature. So we're going to bunch it up and say that that is equal to K prime, just so that we know it's another constant, times A. That right there is your overall rate law, right there. Why? Because look at that overall rate law. It now has chemicals that is part of your overall stoichiometry. It doesn't have intermediates. Now we can say that the overall rate law is first order in A, unimolecular. You have to know a little bit of algebra when your rate determining step is not the first step. It's the second or third step. Second or third step, you need to make substitution for that intermediate based on the other chemicals in the previous step. Okay, let me clear this. And so that's basically what we have right here. I'm kind of like telling you what I just did. And then here is the derivation of that. And here is another example. This is easy. Why? Because the first step is the slow step. I can just write the rate law. Whenever the first step is the slow step, consider it a gift. You can write the rate law. K equals NO2. Oops. Rate is equal to K times NO2 and O3. It's basically what reactants are in that slow step, to the first. First order in NO2, first order in O3, second order overall bimolecular. Here, it's a little bit more tedious. It's a little bit more tedious, but we can start by writing this. We can say that the rate is equal to N2O4. Let's not forget our K and O3. But notice N2O4 is an intermediate. N2O4 is an intermediate. So you can't have N2O4 in your rate law. This cannot exist. So what do? We look at the first reaction and we write the equilibrium expression. The equilibrium expression is equilibrium equals products, N2O4, taken to the first power. Why first power? Because there's only one right there. You got to make sure that the reaction is balanced. Products over reactant, NO2 squared. There's 2 NO2. Now I'm going to rearrange this equation and say N2O4 is equal to K equilibrium times NO2 squared. And I'm going to substitute this whole thing right here in for that. It's an algebra problem from this point on. And then if I do that, rate is equal to K. Then I'm going to plug this in, K equilibrium, NO2 squared. But let's not forget O3. And this is equal to K. Remember, we're going to bunch up these Ks. NO2 squared O3. That right there is your rate law. That right there is your rate law. It's a math problem. It's not calculus. Okay, so you guys can do this. You can. That would be your rate law. That's how you would work these problems. You have to make substitution. And this is the work. I think I'm going to leave it at that and then continue on next time. But let me just show you this work right there. This is the work right here. Rate is equal to NO2 squared O3 term molecular. Second order in NO2, first order in O3. That's your rate law. Notice that NO2 is going to be in your net reaction. Your net reaction, it has NO2 in it. O3 is also in your net reaction. So that's allowable. Okay, that's allowable. Here's another example. I'll continue with this next time, but I'm going to call it a day. You guys can take a look at it. You can basically just kind of see what's going on here. Again, the first step is a slow step, super easy. Okay, super easy. Here's an example in which the second step is a slow step, a little bit more complicated, but you guys should be able to get through that. This is a problem that you guys can see the solution to right here, but I really want to do this. This was supposed to be reserved for class, but what I want to do is just kind of show you how to work this problem, just because I noticed that some people are struggling in terms of doing some of these types of problems. So I want to give you the thought process in doing these types of problems. Okay, this reaction is actually the synthesis of phosgene. This chemical right here is phosgene. And phosgene was a gas or a chemical that was developed in World War I. And the both sides that were fighting in World War I were using this chemical. What happens is they like mustard gas. This particular chemical would be put in some sort of a device thrown to the enemy, and then the gas would be released. And you can see right away that this chemical has chlorine and CO. Okay, it's actually this structure right here. So you can see it's trigonoplanar in its geometry. And when you breathe it in, it breaks down to chlorine gas and carbon monoxide. Carbon monoxide is bad enough. Carbon monoxide does is it displaces the oxygen in your hemoglobin and then takes that site. And of course, what happens if you don't get oxygen in your cells is that you basically are suffocating. And then chlorine gas will get into your lungs, and it will basically dehydrate, and it makes the fluid come out in your lungs, and you basically drown in your own fluids. But anyway, enough history on that. What I want to show you is the different steps that you usually get in these types of problems. What is the overall reaction? What is the intermediates and catalysts? What is the rate law from this mechanism? What is the order of this reaction with respect to each reactant? What is the molecularity, and how would doubling the concentration of CO affect the reaction? So let's take a look at those. Okay, so first thing we want to do is just write the reaction. So I'm going to write the reaction right here. It's going to be H plus Cl2 in equilibrium. Whenever you see that double arrow, it means it's equilibrium. That means that the forward reaction occurs at the same rate, speed, as the reverse reaction. Okay, and this is Cl plus HCl. Now, remember what I told you. Never assume that a reaction I give you is balanced. So double check, make sure it's balanced. This is a balanced equation. You've got 2 chlorines on both sides and a hydrogen on both sides. Okay, then we have HCl plus CO in equilibrium again. We have ClCO plus H plus. Okay, notice that the H plus is consumed in the first step, but it's regenerated in the second step. Hint. And then we have ClCO plus Cl goes to Cl2CO. Okay, so this is step number 1, this is step number 2, this is step number 3, and I tell you that step number 3 is the slow step, which means that that's where you need to start your work. That's where the rate law comes from, but that is not necessarily the answer to the question. Let's just balance this equation first. Okay, change my pen here. Now, if you take a look at this, that is produced in the first reaction and then consumed on the second. That's an intermediate. So we can say intermediate so far is HCl. Okay, this also is produced in the second reaction and consumed on the third reaction. So that's ClCO. That also is an intermediate. Okay, and then let's also take a look further. You can see that this chemical, and again, it's not difficult. You just have to make sure that you have a keen eye on finding these things. Produce in the first, consume in the third. That is also an intermediate. Change my pen here. And let's take a look at this. That is starts on the reactant and then consume. So the catalyst in this particular case is going to be H plus. Okay, it's introduced and then consume and then reappears. That's catalyst. All these are balanced. So the net reaction here is, let me change my pen here. The net reaction would be this right here. You've got Cl2 plus CO goes to Cl2CO. That's your net reaction. Okay. Now, let's continue on with the rate law. In the rate law, we always work on the rate determining step, and that's step 3. The rate determining step is the slowest step. And you can get a hint that it's the one with only a single arrow, okay, in general, but it should be specified in the question, or you can tell if it's the rate determining step because in your reaction profile diagram, it's the one with the highest transition state, okay? It's the one with the highest transition state. So that is the third step. This is a 3-step mechanism. Third step is going to have the highest transition step. That's the rate determining step, RDS. It doesn't matter that this activation energy, the third step, is smaller than this activation energy in the first step. Doesn't matter about that. You do know that activation energy 1 is greater than activation energy 3 just from that diagram. The fact is the transition state's the highest energy. So you need a lot of energy just to get to that highest peak. That's your rate determining step. Okay. So it's important that you remember that. The step which has the highest energetic transition state or the activated complex is going to be your rate determining step. It's going to be your slow step. So we're going to base our rate law based on that third step. So we start with rate, and the rate is going to be a speed, something molarity per second, per minute, per hour, depending on the time you're measuring, okay? But it's a concentration per time, and that is equal to K. And you don't know K at this point. You can figure out K based on the Arrhenius equation, okay? But you know that there is a rate constant in there. all rate laws will have a rate constant, even zeroth order. And we base the chemical that we're going to write our rate law based on that third reaction, that third elementary step, and it's the reactants in that third elementary step. And so that's ClCO and Cl. Now notice that Cl, Co, and Cl are both intermediates. So you can't write that as your answer. That's not allowed. The only thing that is allowed in your rate law are the reactants in the reaction and the catalyst. Okay, so these are intermediates. You need to modify this rate law further. So the way we do that is we look at the previous step and we write an equilibrium based on that previous step. And that equilibrium would be K equilibrium 2 is equal to products, okay, ClCO, that's the products. These are the products right here. H plus over reactant. And these are the reactants over here, okay? Now, depending on the coefficient of these, you would raise it to the appropriate power. If there was a 2 in front of this, for example, then you would raise this to the second power. But there's just, when you don't see a coefficient, it's implied it's 1. And so anything to the first power is just that same chemical, okay? So this is your equilibrium expression for the second step. Now, remember that this right here has, we need to substitute for ClCO. So we need to solve this problem for ClCO, okay? And we can do that by doing a simple algebra. What we want to do is take all these variables to one side and isolate ClCO. So we do that. If you are having problems doing this algebra, you're going to have serious problems in terms of going along in this class, because everyone should be able to do simple algebra in this course. So that's equal to K equilibrium 2, and that's not an equal sign, that's a derivation. You got CO and you have HCl. Okay, so these two right here go up in the numerator, and then H plus goes in the denominator, like that. That we're isolating this chemical right here. Okay, we're isolating this chemical right here. So we can take all of this now and plug it in here. And when we do that, we have K equilibrium 2. And then let's just write all these. We have a CO, HCl, H plus. But we also have a Cl up here, okay, from this previous problem. So all we did was substitute for ClCO, okay? Now, look at this problem, and this is equal to rate again, and look for what's not allowed on that. That right there is not the finished product. You got to see that there's a couple more intermediate in here. The intermediate's HCl, this guy right here, and it looks like Cl as well is in here. Those are intermediate. They are not allowed to be in the rate law. So the next step would be to look at the first equilibrium, and we can do that by doing this. First equilibrium is K equilibrium 1 is equal to products over reactant. Okay, and in this particular case, I'm going to do a little trick. I'm not just going to substitute for HCl and solve it here. you actually have HCl and Cl. So I'm just going to take this and leave it as is, and then simplify this equation. And when I simplify this equation, then I have K equilibrium. 1 is equal to what we have. Oops, let me go back. And the reason why I need to go back is because this is not quite what's going to happen. So when we bring this 2 over here, what we have is K equilibrium 1 times H plus times Cl2 equals Cl and HCl. And why did we do that? Because these two are intermediate, and now we can substitute right here. Okay, we can substitute right here. And when we do that, again, it's algebra. We can write the rate law like this. This equilibrium. We still have CO up here and H plus down here. Okay, and then we also have K equilibrium 1. That's what I wrote right here. And then H plus and Cl2. And you can see the H plus cancels. Okay, so what we have is basically the rate law is going to be, all this is just a constant times a constant times a constant is just another constant. You got to remember that. Otherwise, it's going to drive you nuts to carry all those K's. That's just K. And this simplifies. I'm going to have to clean my slate because my iPad doesn't do pages. So when it's a blank slate. So let me just erase this so that I don't delete all my work. Okay, let me just erase this so that you guys can see what's going on. So your final rate law is going to look like this. Rate is equal to K, CO, Cl2. That's going to be your final rate law right there. It simplifies because what you're doing is you're substituting for the intermediates. Don't substitute for a callus. Callus can be in the rate law. Intermediates cannot. So that's going to be the solution. You're going to see that it's first order in CO, first order in Cl2, second order overall. Okay, and I think that takes care of that. Let me just flip out of this. This of course will be erased, but I believe this session is being recorded, so I think we are good. Okay, yeah, I can see that it's being recorded. Please keep in mind that I generally record the session for your benefit. If, again, you don't want to be recorded, just change your name and blank your camera. So let me go ahead and do this. What is the overall order? That's second. What is the intermediate and the callus? We already looked at that. What is the rate law for this mechanism? We saw that it was rate is equal to K, CO times, I believe, Cl2. What is the order of the reaction with respect to each reactant? First order in CO, first order in Cl2. What is the overall molecularity? 1 plus 1. First order in CO, first order in Cl2 is 2. Second order overall, molecularity is bimolecular. How would, because the rate is this right here. Okay, when you double the concentration of CO, you also double the rate. If it was squared, if you double the concentration of CO, you quadruple the rate. Okay, That's assuming that chlorine concentration is not changed and then K doesn't change. So that's how you would solve this type of problem. It's a little bit more involved in that, yeah, you have to work with 3 equations, but it's not that difficult. Okay, it's not that difficult. So you guys should be able to attack those.
Professor?
Yes.
So for that last one, how would doubling the concentration of CO affect the reaction? The only thing that you change, so initially it was KCO, concentration of CO, concentration of diatomic chlorine, and so that way it would double. But when you put a 2, that's when it would quadruple.
Yes, exactly. But that wasn't the rate law. But if it was 2, if that was what we would do, it would be in this particular which isn't the answer to this problem, just so that you know, but suppose
Right.
that was a square there, then it would be second order in CO, first order in Cl2, third order overall, and then anything like 2 to the 2 is 4, 3 to the 2 is 9, that's a quadrupling.
Okay.
Okay, in this particular case, because we're saying it's doubling. So if we go from 1 to 2, that'll make it in this particular case 4. So yeah, you just have to look at the math in that case.
Thank you.
Okay. All right. So that pretty much takes care of this. And I hope that with this solution, you guys will be able to do the activity worksheet in terms of that first problem where I give you, I think it's hydrogen and iodine or something like that. I forget what, but it's a 3-step mechanism. And the third step is the rate determining step. If it's a 3rd-step mechanism and the first step is the rate determining step, don't even bother looking at the 2nd and 3rd because you're never going to use that. The rate's going to be determined by the slowest step. And what happens is the speed of the reaction will be impeded by that first step. And then once it passes that, the 2nd and 3rd just goes. You're not even going to solve the problems. You're not even going to use the reactions from the 2nd and 3rd because that's after the first step. So don't put more work on yourself and think that you have to solve the whole algebra. If it's a 2nd step, don't bother looking at the 3rd. You probably need to look at the 1st and the 2nd. Okay, and that's what general chemistry students do. They look at a problem and they reach and make it harder than it is. And that's a classic example that I've seen in the past where I give you a mechanism and I tell you it's a 2nd or maybe the 1st as the rate determining step. And folks would just start with the 3rd and start solving for that. You're basically driving yourself in the wrong direction. So please keep that in mind. The rate determining step is the key in determining the rate law. Okay. And only reactions before the rate determining steps are going to be useful to you. So this just is a summary of kinetics. So let me summarize what we talked about in kinetics. We talked about rate, the speed of the reaction. How do we calculate it? We calculate rate based on the change of the concentration with respect to time. Okay. If we have a rate and we have the stoichiometry, then we can give the speed of the reaction of each of the chemical in the stoichiometry based on the coefficient. And that's just the speed. That's not even the rate law. That just tells you how fast they're consumed and how fast they appear. If they're consumed, it's negative. If they appear, it's positive. So we started with that, and we did that with acrylonitrile. Then we gave you the concept of the methods of initial rate. Methods of initial rates is an experiment now in which we do a series of experiments in which we determine the rate based on varying the concentrations of the reactants. It's only the reactants. We don't really monitor the product, but we vary the concentrations of the reactants in a series of experiments, and we see how the rate changes. And we only allow that reaction to take place like 3% of the length of time before the reaction reaches equilibrium. Reactions don't really come to an end, they reach equilibrium. So we look at maybe 3% or less of the time by which the reaction reaches equilibrium, and then we look at the concentration change and the rate by which the concentration changes with respect to time. And based on that, we can say that, yeah, this chemical influences the rate based on maybe to the first power. If we double it, then the rate doubles. Or maybe this concentration is not influential in the rate. So it's going to be 0th order. So that's what we did in terms of the methods of initial rate. Then we went to look at 3 simple case, 0, first, and second order kinetics. And what we did was we started with the integrated rate law, where we said that, okay, that the concentration, the change in the concentration is equal to K times the concentration of the chemical to the first power, or the concentration of the chemical to the 0th power, or the concentration of the chemical to the second power, okay? 0, first, and second order. You could also do it for third order, okay? That's more rare, but if you are a chemistry major, then you might cover that in your PChem class. But all we did was 3 orders, 0, first, and second. And for those of you who are doing lab this week, it's very pertinent to the lab because that's what you guys are going to be analyzing in terms of methobiology. Anyway, we derived the equations based on separating the variables and integrating it. And what you need to do is you need to find equation, and it's found in the back of your lab manual or in your textbook as well, because when you have a 0, first, or second order, then it follows an equation in terms of y equals mx plus b. And if you have a series of data and you plot it depending on 0, first, and order, the 0th order, the concentration versus time, T now is time, not temperature, time, you get a straight line. And the slope, the negative slope is the rate constant. First order is the natural log of the rate constant versus versus time. The slope, the negative slope, is going to be your rate constant K. That's how you determine K in these things. And then second order, the reciprocal of the rate constant K, 1 over K, over versus time. The slope will be positive in this case, but the slope, okay, is going to be related to your rate constant. So we just looked at 0, first, and second order in this particular case, and they have specific solutions that you can find. Don't bother deriving it. Use the solutions. And graphing the data, depending on whether it's 0, first, or second order, will give you information. You should also know the equations for the half-life, if it's 0, first, or second order. 0th order and second order, the half-life is a function of the initial concentration. First order, the half-life is not a function of the concentration at all. It's 0.693 divided by K. So keep that in mind, especially when we get to radioactivity. Then after that, we talked about the Arrhenius equation. Arrhenius equation is the equation that tells you something about the speed of the reaction. The Arrhenius equation gives you information about activation energy. The Arrhenius equation gives you K. K is the solution to the Arrhenius equation, or the Arrhenius equation is the solution to K, the rate constant. Okay, K is equal to A, that's your pre-exponential factor, times E exponent minus EA, which is activation energy, over RT. That factor, E to the minus EA over RT, gives you the weighted amount of chemicals that can overcome the activation barrier. That's basically what we have there. And then the last concept in chapter 14 is mechanisms, kinetics. And when you put all that together, you get basically that worksheet that I gave you. The reaction coordinate diagram, the different elementary steps, how the energetics of the different elementary steps relate to the transition state, the intermediate, the delta H overall, and how you can use the different steps to figure out which is the rate determining step and then come up with the rate law. Okay, so that's why I like the worksheet because it brings a lot of it together. It brings the concept together, and it's not just concepts that are uh, not related to each other. These things are related to each other, and if you can see the overall picture, then perhaps you can understand where kinetics and why kinetics is important. Okay, so that's just a summary of what we covered in chapter 14. So